Welcome to this Math 1060 review for Exam 3. We will go ahead and get started. Okay, so I'm starting with some properties of vectors. So if we're given vectors v equals v1, v2, and w equals w1, w2, then we start with the magnitude of v, which is written with a double bar on both sides of the vector v. The magnitude of v is equal to the square root of v sub 1 squared plus v sub 2 squared. And then if we move on to the next property that we're interested in, the unit vector in the same direction as the vector v can be found by taking the vector v and dividing it by the magnitude of that vector v, okay? And then the dot product of the vectors v and w, v dot w, is equal to v1 times w1 plus v2 times w2. The geometric interpretation of the dot product, v dot w, is equal to the magnitude of v times the magnitude of w times the cosine of theta, where theta is that angle between the vectors v and w. And we can go a little bit further with that. If we divide both sides by magnitude v, magnitude w, we get cosine theta equals v dot w over the magnitude of v times the magnitude of w. All right, and then if we're trying to find what that angle is, which is often the use of this particular interpretation of the dot product, we can use the cosine inverse, and the angle between the two vectors would be equal to the cosine inverse of v dot w divided by the magnitude of v times the magnitude of w. And we'll use all of these properties in just a minute. I wanted to make sure that we kind of go over the things you need to know for this exam that's coming up soon. Okay, so the first thing we're going to do is we're going to find a magnitude. So in this problem number 1, we're given the vector v, which is equal to the vector -1, -5. We want to find the magnitude of v. Well, we do that by taking the square root of the first component of v, which is -1 squared, plus the second component of v, which is -5 squared. This simplifies to the square root of 1 plus 25, and we have a magnitude of square root of 26. All right, and then we go on to finding a unit vector having the same direction as v. We usually write a unit vector with a little caret top on top to indicate that it is a unit vector. And to find the unit vector, we take the vector v, we divide it by the magnitude of that vector v. I usually think of this as 1 over the magnitude of the vector times the vector itself, and in this case that would be 1 over the square root of 26 times the vector v, which is -1, -5. But we don't want to leave it like this. We want to distribute 1 over square root 26 through to our vector to multiply with using scalar multiplication. Here we end up with -1 over square root 26, -5 over square root 26. Okay, and we have our unit vector. We could check that that is a unit vector if you wanted to. To check, you just make sure that the magnitude of this vector is equal to 1, which you'll find that it is if you try this. Okay, we just want to make sure that's equal to 1. All right, so let's go on to our next problem here. And the next problem, number 2 here, we're given two vectors, v equals 3, 4, and w equals -1, -2. We start by finding 3v minus w, which I'm going to think of as 3 times the vector v, the vector 3, 4, plus a -1 times the vector w, which is -1, -2. And that would give us, distributing these scalars through, we would have 9, 12, plus 1, 2. Adding these two vectors together, then 9 plus 1 is 10, 12 plus 2 is 14. Okay, and hopefully you are familiar with scalar multiplication. We take 3 times 3, then 3 times 4 to give us this vector 9, 12. And we did the same thing with the negative 1 here as a scalar. Okay, if we want to take v dot w, we take the first component of v, which is 3, times the first component of w, which is negative 1, plus the second component of v, which would be 4, times the second component of w, which is negative 2. We get negative 3 minus 8. That would give us negative 11 for the dot product of these two vectors. Okay, and there's a third part to this, and so keep in mind here we found v dot w is equal to negative 11. I made a separate slide here so that we could make use of a little more space. So if we're given these two vectors that we had in the previous problem, we want to find the angle between the vectors, and we know that v dot w equals negative 11. Well, we found a minute ago that to find the angle between the two vectors, we take the cosine inverse of v dot w divided by the magnitude of v times the magnitude of w. Well, let's go ahead and see if we can, the magnitude of v, right here is our vector v, we'd take the square root of 3 squared, which would be 9, plus 4 squared, which is 16. We get the magnitude of v is equal to the square root of 25, which would give us 5 there. Okay, and then we find the magnitude of w, which would be the square root of negative 1 squared plus negative 2 squared. We'd get the square root of 5. Okay. So let's go ahead and see if we can solve for theta. Theta then would equal cosine inverse of v dot w, which we found to be negative 11, divided by the magnitude of v, which is 5, times the magnitude of w, which is square root of 5. Okay, and so we have the cosine inverse of negative 11 over 5 square root 5. If you plug that in a calculator, you should get approximately, and we're rounding to the nearest hundredth here, so you'd get approximately 169.70 degrees. And when we're talking about vectors, we usually do use degrees here. So this should be the angle between those two vectors, 169.70. All right. So let's move on. We have one more problem here with vectors, it looks like. The next thing we're doing is looking at two vectors. These vectors are v equals negative 3, 4, and w equals 8, 6. We want to determine if these vectors are orthogonal. Well, there is only one way that vectors will be orthogonal, and if that is if v dot w is equal to 0. So let's see what the dot product of these two vectors is. So we'd take the first component of v, negative 3, times the first component of w, which is 8, plus the second component of v times the second component of w. We get negative 24 plus 24, which gives us 0. That's all we have to do to show that two vectors are orthogonal, show that their dot product is 0. And if you want to verify why that works for yourself, go back and look at how we found the angle between two vectors a minute ago, and you'll see that that follows. And so we would, I guess, answer this yes, as long as we've shown all our work here. Okay, moving on. Sketch the set of parametric equations for the following parameterization. And we have x equals 4 sine t, y equals 3 cosine t, for pi halves is less than or equal to t is less than or equal to 3 pi over 2. Let's look at a little chart here. I started this just to save some time because this takes a lot of writing down. So let's go. We have a chart. We list the values for t going from pi halves to 3 pi halves with a few critical points here in between. And so starting with t equals pi halves, x is equal to 4 sine t. The sine of pi halves is going to be 1, right? So the sine of pi halves is 1. We take 4 times 1 and get 4 for an x value. I think I'll go through all the x's here first. Excuse me, and then we'll move on to y. So for 3 pi over 4, we're in quadrant 2. In quadrant 2, the sign is positive, and the sine of 3 pi over 4 would be square root of 2 over 2. 4 times square root of 2 over 2 is going to leave us with 2 square root 2. And then we move on to a t value of pi. The sine of pi would be 0. 4 times 0 is 0. That one's easy. 5 pi over 4, we're in quadrant 3. In quadrant 3, the sign is negative. We're going to have 4 times negative square root 2 over 2. And simplifying that would give us negative 2 square root 2. Then 3 pi halves. The sine of 3 pi halves would be equal to negative 1. 4 times negative 1 would give us negative 4 here. Okay, so we have our x values. Then moving on to the y values, the cosine, and usually, cosine goes with x, sine goes with y, but in this case, it doesn't really matter if we're just using the sine and cosine values to find x and y coordinates. If it's defined this way, we have cosine going with y this time. So for pi halves, the cosine of pi halves would be 0. 3 times 0 would give us 0. The cosine of 3 pi over 4, we're in quadrant 2 where the cosine is negative, so we're going to have 3 times negative square root 2 over 2, and we could write that as negative 3 square root 2 over 2. Then at pi, the cosine of pi is negative 1. 3 times negative 1 would give us negative 3 here. For 5 pi over 4, we're in quadrant 3. In quadrant 3, the cosine is negative, so we're going to have 3 times negative square root of 2 over 2 again, leaving us with negative 3 square root 2 over 2. And then finally, for 3 pi halves, the cosine of 3 pi halves is 0, and then 3 times 0 again gives us 0 here. It's going to help a little bit, I think, if you could use a calculator to approximate here a bit for when we're going to graph here. So negative 3 square root 2 over 2 is approximately negative 2.1. And then 2 square root of 2 is going to be approximately equal to 2.8. Right here, this would be approximately equal to negative 2.8. Okay, so I have a graph here, and let's go ahead and graph these points that we have. So we're just plotting the x and y values here, and when we're graphing a parametric equation, a set of parametric equations, we have a direction that we're going, so we're going to pay close attention to that. We start at the point 4, 0, and then we move on to the point that's about 2.8, negative 2.1. Oh, let's say about right here somewhere. And so we're moving along here, and we're going to put arrows on our curve as we go. So we are paying attention to the direction here. Then we move to the point 0, negative 3. And again, moving along, we're going to put some arrows here to give us direction. We move on to about negative 2.8, negative 2.1. Oh, about right here somewhere. And so moving along, adding arrows for direction, and we end at negative 4, 0. So we'll go ahead and finish off our graph here. And that's it. Okay, so this is as far as we go. And we've indicated the direction, the starting place, the ending place this graph would would take on values for. And so let's go on to the next problem. Convert the polar coordinate 5, 7 pi over 4 to a rectangular coordinate. And there's a note here that this is not a complex number. And the reason that I added that little comment is that often students, when they're converting between polar and rectangular coordinates, they assume everything is a complex number and throw i's in. There's no I here. This is just a number that's graphed in the polar plane, and then we're going to graph it in the rectangular plane. Or we're not going to graph it, but we're going to find the coordinates that we'd have if we did graph it in the rectangular plane. And so in the polar plane, our coordinates are r, theta. In the rectangular plane, we're going to be plotting x and y values, or we're going to find x and y values. Okay, so let's do it. The first thing I would do is, well, I'm going to use some formulas that I happen to know. I happen to know x equals r cosine theta and y equals r sine theta. So in this case, x is going to equal 5 cosine of 7 pi over 4, and y would equal 5 sine of 7 pi over 4. So x is equal to 5. The cosine of 7 pi over 4 is square root of 2 over 2. We're in the fourth quadrant, so the cosine's positive there. We get x equals 5 square root 2 over 2. And y is going to equal 5 times the sine of 7 pi over 4. In quadrant 4, the sign is negative. Negative square root 2 over 2. We end up with y equals negative 5 square root 2 over 2. And so our rectangular coordinates would be, if we did graph this point, it would be the point where x is equal to 5 square root 2 over 2. Y is equal to negative 5 square root 2 over 2. Okay, and that is this problem. Let's move on. And we're looking now, we have a few more rules here, or things that are good to have in your mind when you take the exam. We're looking at polar rectangular representations for complex numbers now. So we are looking at complex numbers. The rectangular form of a complex number is z equals a plus bi. And if we want to look at the polar form, we have z equals modulus of z cis theta, or z equals modulus of z cosine theta plus I sine theta. What cis means is basically cosine theta plus I sine theta. And so the other thing we want to look at, we have some handy formulas here. And the first one being the modulus of z is equal to the square root of a squared plus b squared. The second one I have here is that tangent of theta equals b over a, or the imaginary part of z divided by the real part of z. And so we'll use these formulas when we're working on these problems in just a minute. The other thing we're going to need before we go on to our next problem we're going to solve, though, is we're going to need some formulas for products, quotients, and powers. So if we're given that z equals the modulus of z cis alpha and w equals modulus of w cis beta, then we're going to use the product rule, which would be zw equals modulus of z times modulus of w cis alpha plus beta. The quotient rule is similar to the product rule, but we're dividing here. So z over w is equal to modulus of z divided by modulus of w cis alpha minus beta. Okay, and then we have the power rule, also referred to as de Moivre's theorem, which is z to the power n, where this is our z here, is equal to the modulus of z raised to the power n cis n times our alpha, where n is equal to 1, 2, 3, whatever integer you want to choose past 1, 2, 3. So you could use, I guess, if you wanted to go to the 90th power, you could go there. Let's calculate a power here. And we have here, we're calculating negative 5 plus 5i raised to the third power, and we're going to give our answer in the form a plus bi, noting now that we do have a complex number, which should be obvious being that we have an I here. But what we're doing is we're raising some number z to the third power, where z is equal to negative 5 plus 5i. Well, before you can use the formulas we just pulled up on the last screen, you need to make sure that you're in polar form with your original coordinates. And so this right here is rectangular form. And so we need to change this into polar form before we go any further. And the first thing I want to do to change a rectangular form coordinates into polar form is I want to find the modulus of z here, which would be equal to the square root of negative 5 squared plus 5 squared, a squared plus b squared, and that would give us the square root of 25 plus 25, which is the square root of 50. We can simplify that a bit by writing modulus of z is equal to 5 square root 2. Okay, so we start by finding the modulus of z, and then we want to find the angle that we're, so in polar form we need r and we need theta, right? So we need to find theta. So I'm going to use the fact that tangent theta is equal to the imaginary part of z over the real part of z. In this case that would be negative 1. But in addition to knowing that tangent of theta is equal to negative 1, to figure out what theta is equal to, we need to figure out what quadrant we're in, because there's two different quadrants where the tangent is equal to negative 1. Well, looking back at z here, we have negative 5 plus 5i. So we're going to be here in quadrant 2. In quadrant 2, if the tangent is equal to negative 1, I'm going to have a reference angle of pi fourths, right? But to find the angle theta itself, the angle theta itself would be pi minus pi fourths, or 3 pi fourths. Okay, so we have theta equals 3 pi fourths. That gives us our polar form of z would be equal to 5 square root 2 cis theta, which in this case is 3 pi over 4. Okay, we have the hardest part done. So we have z in polar form. And now we're going to take z and we're going to raise it to the third power here. So z cubed is going to equal, we take the modulus of z, which is 5 square root 2, and we cube the modulus, cis, and then we're going to take that number 3 and we're going to multiply 3 times our argument. So we're going to have 3 times 3 pi over 4. That gives us z cubed is equal to 5 cubed, which would be 125, times square root of 2 squared, times square root of 2. If you think about it, as we're cubing here, cis, and we're going to have 9 pi over 4. Okay, so we'll just simplify a bit further. We have z cubed equals 125 times 2 is 250, so I have 250 square root 2 cis. The problem with 9 pi over 4 is that this is outside our range from 0 to 2 pi. And so 9 pi over 4 would be, where would we get there? We'd go around 8 pi over 4 would take us here. And then 1 more pi fourths would take us into the first quadrant where we would have an angle of, so a coterminal angle with 9 pi over 4 is pi fourths. And that's how we want to write our z cubed. And we have 250 square root 2 cis pi fourths. This is actually the polar form, and we're asked to put our answer in the form a plus bi. That's really fairly easy to do. I think it's easier going this direction than the other. So we'll go ahead and do that. Z cubed is going to equal 250 square root 2. And all we do is rewrite cis with what it's standing for. Cis is standing for cosine of pi fourths, or cosine theta, plus I. Cis theta is cosine theta plus I sine theta. Here our theta is pi fourths, so we have cosine pi fourths plus I sine pi fourths. Okay, and then we'll continue simplifying. We have 250 square root 2. The cosine of pi fourths is square root 2 over 2, as is the sine. And then distributing 250 square root of 2 through. Notice square root of 2 times square root of 2 over 2 is the same as 2 over 2 or 1. Okay, so we can kind of ignore the square root 2 part of this. We're going to be left with 250 plus I, and again we have square root 2 times square root of 2 over 2 times 250. So we're left with 250 plus I times 250. Usually we write, actually this is a correct answer, but in this class we're writing A plus BI when B is an integer. So we're going to write Z cubed as 250 plus 250I. And we have it. All right, let's go on. Lots to do today. We want to look at the law of sines, which I'm just putting this here to make sure you know what you need to know. For the test that's coming up, you'll need to know the law of sines. We can draw any old triangle we like. And if we have a side of length A, a side of length B, a side of length C, where A is opposite the angle alpha, B is opposite the angle beta, C is opposite the angle gamma, then sine alpha over A equals sine beta over B equals sine gamma over C. And so we're going to use the law of sines in our next problem here. In this problem, we're assuming that alpha is opposite side A, beta is opposite side B, and gamma is opposite side C. We want to solve the resulting triangle if possible and round each answer to the nearest tenth. So let's go ahead and sketch a triangle here. And I'm not trying to get any of the measurements accurate in any sense of the word. And so we're told that alpha equals 55 degrees. We'll just pick some angle and call it alpha. We're told that gamma equals 72 degrees. And we're told that B equals 20. So B would be opposite our angle beta. So here we have B equals 20. The side A is opposite alpha, side C is opposite gamma. And so in solving, we're going to use the law of sines here. Where I want to start at is, for the law of sines, we need to know a side length and the opposite angle measure. Well, we can find the measure of beta pretty easily here. Beta is going to equal 180 degrees minus alpha minus gamma. And so we get beta is equal to, let's see. Oh, wait. I wrote that wrong, didn't I? Okay, I'm trying to find my eraser thing here. This is not good. Okay, well, I'm not finding my eraser, so I'm just going to change this to 72 degrees, okay? So we have 180 degrees minus 55 degrees minus 72 degrees, and we get beta is equal to 53 degrees. Okay, so we got beta, and so we've solved in solving a triangle, that means we want to find all the missing angles, all the missing side lengths. So we have beta. Now that we have beta, we can use the law of sines. I can look at taking the sine of beta, which is 53 degrees, over the side length B, which is opposite beta, would be 20. And let's go ahead and let's find C. So to find C, we're going to have sine 53 over 20 equals sine of 72 degrees over C. we'd cross multiply. We'd get C sine of 53 degrees equals 20 sine of 72 degrees. We'll divide through by sine of 53 degrees. We get C equals 20 sine of 72 degrees divided by sine of 53 degrees. Go ahead and try this in your own calculator. I got C is approximately equal, and we're told to round to the nearest tenth. That's important on your exams because the exams are built so that they look at the exact decimal place you're supposed to be rounding to. So here C is approximately equal to 23.8 degrees. Okay, so we got C. And now, what are we left to find? We need to find length A, it looks like. So to find length A, again, we can take sine of 53 degrees over 20. This time, though, we're looking for A is being opposite the angle 55 degrees. So sine 53 degrees over 20 equals sine 55 degrees over A. We cross multiply and then divide through by sine of 53 degrees. So we're going to end up with A equals 20 sine of 55 degrees divided by sine of 53 degrees. And if you do that, you should get that A is approximately equal to 20.5 degrees. And that's what it means to solve this triangle. Now we know every angle and every side length, and so we can move on to our next problem, maybe. Except that my screen is freezing up here, so that's not good. Let's see if I can. Okay. I may have to, I'm trying to use this as a tablet. I'm putting it back now. So let's see if we can now go to the next slide. Okay, so we have the law of cosines next, which is a squared equals b squared plus c squared minus 2bc cosine alpha. And then we have two other versions of this. I would prefer actually not even to have values here, because what we do is we pick some side length A, and we're going to put the angle opposite that side A here. So whatever we start with on the left side of our equation is the side opposite the angle that's being referenced by the cosine here. And so the other two side lengths are here. In this case, b squared plus c squared minus 2bc cosine of the angle that we chose because it matches, it's opposite this side length here. Well, occasionally, maybe you need to know these formulas. And basically, if we drew our usual triangle here, we'd have sides of length A, B, and C. And to fit these formulas, A is opposite the angle alpha, B is opposite the angle beta, C is opposite the angle gamma. Okay, so this is where the triangle would take place here. And now we're going to use that law of cosines to solve this problem. And to solve this problem, we're going to find the distance across a small lake. A surveyor has taken the measurements that are shown in the picture here. We want to find the distance across the lake using this information, and your answer should be accurate to 2 decimal places. Okay, so let's see what we need to do here. Well, we're trying to find this distance right here. Okay, and let me see if I can get my, okay, hold on a sec. I'm trying to pull my computer apart here so I can write a little more neatly. Okay, let's do it. Okay, so to find D here, notice that the side length D is opposite this angle of measure 38.8 degrees. So we're going to solve this problem using D squared. And let's see, I'll go down here where I have some extra space. D squared equals, we take one side length, 2.93 squared, plus the other side length, 1.61 squared, minus 2 times our first side length here, 2.93, times our second side length, 1.61, cosine of the angle opposite D, which is 38.8 degrees. And we're almost done. We almost have D. What I'm going to do here is I'm going to take the square root of both sides. So I'm going to have D is equal to the square root of all this stuff on the right side. And if I do that, I'm going to find D is approximately equal to, paying attention that we're rounding to 2 decimal places, D is approximately equal to 1.96 miles. And again, try this on your own to make sure that you're plugging this in your calculator correctly so that you know you'll get it on an exam. And once again, I'm having trouble with my computer. Well, we'll do what we can. Okay, going on to the next slide here. We're going to use the result that we just found, actually. Well, let's go back and remember what that result was. We found the distance here was equal to approximately 1.96 miles. So we're just going to say that this right here is about 1.96 miles. Okay, so we're going to use the result from the problem that we just did, which I think actually was number 8. Okay, and so we're going to use the result from number 8 to approximate the area of the triangular region. And we need a magic formula for this. Again, this is one you should know, Heron's formula. So we're going to use Heron's formula. So for a triangle with side lengths of A, B, and C using Heron's formula, so we have some triangle. We don't really care about the angles here. We need to know the side lengths, so A, B, and C. The area of this triangle is equal to the square root of S times S minus A times S minus B times S minus C. Where actually the first thing we need to do is figure out what S is. S is the semi-perimeter of this triangle. If you think of what the perimeter would be, the perimeter would just be A plus B plus C. So semi-perimeter is half of the perimeter. And so we take the semi-perimeter S and then we plug it into Heron's formula here. Well, we'll use this formula to solve the problem that we have. And so the first thing with this problem is we know our 3 side lengths. We're trying to find the area of this red triangle. And so we find that S is going to equal here 1/2 times, well, let's take 1.61 as our first side length. We'll take 1.96 as our second side length. And then we're left with 2.93 for the third side length. And we get S is equal to, and I have 3.25. Okay, so we have S equals 3.25. So now, using Heron's formula for area, the area is going to be equal to the square root of, and this takes some writing, we start with S, which is 3.25, times S minus our first side length, 3.25, minus 1.61 times S, 3.25, minus our second side length, which is 1.96, times S minus our third side length, 3.25 minus 2.93. Okay, and I guess I didn't need that whole square root, but when you plug this in a calculator, and we're rounding this time to 1 decimal place, we're going to have A is approximately equal to, let's see, I got about 1.5. And notice area is square miles. So let's write this. Area is approximately equal to 1.5 square miles here. And that would be our solution. Okay, moving on. We have Andrew setting off hiking here. So Andrew sets off hiking from the lodge at a bearing of south 75 degrees west. I've gone ahead and put the picture in here. So let's talk about the pictures we're going along. Trying to draw these things while I'm going through a problem is kind of hard on these screens. So Andrew sets off hiking from the lodge at a bearing of south 75 degrees west. So he starts going south and then 75 degrees west here after 2 miles. So he goes in that direction for 2 miles. After 2 miles, he changes to a bearing of from going south to 15 degrees west. So this little measure here is 15 degrees. And then he hikes an additional 3.5 miles. And then what we want to do, first of all, is find his distance from the lodge. So to where he ends up here, we want to find what the distance is from the lodge at that point. So let's just start with that and see what we can do there. I added another little sketch here of the triangle by itself, which is kind of useful, I think, for solving. So on this triangle over here by itself, let's put the 2 miles that we know of, the 3.5 miles, and let's put our distance D. Okay, and what we need to do to solve for D, we're going to use the law of cosines. So I'm going to try to find what this angle, this big angle right here is. So to find that big angle, I'm going to look back at what we've got going on over here. So if you notice, I'm going to come across here and I'm going to sketch a right triangle here. So this also gives us a right angle down here. So if we're trying to find this missing angle, we know that we have for sure the 90 degrees. They're in the middle there. So we have this 90 degrees plus we went from south 15 degrees west. So this little angle here is 15 degrees. And then we need to figure out what this angle right here is. Well, if I look at this right triangle that I've sketched here, I know that this angle here comes from going south 75 degrees west. So this angle that we have here going all the way over is 75 degrees. This is a right angle, so this is 90 degrees. So if I take 90 degrees plus 75 degrees plus whatever this measure is, I should get 180 degrees. So if we took 180 degrees minus 75 degrees minus 90 degrees, I'd get the measure of this missing angle here, which would be 15 degrees. Okay, so we have 15 degrees plus 90 degrees plus 15 degrees. That gives us what, 120 degrees, I believe. And so we can replace our little arrow there with okay. I'm going to replace this little arrow with 120 degrees, from which, using the 120 degrees that we now have, and we can see that 120 degrees is opposite the length D that we're trying to find, we can use the law of cosines. So I'm going to have D squared equals a second side squared plus a third side squared. So then minus 2 times the length of that second side times the length of the third side, cosine the angle opposite our length that we're looking for here, and so that would be 120 degrees. So we have D squared equals 2 squared plus 3.5 squared minus 2 times 3.5 times cosine of 120 degrees. And we can take the square root there. If I take the square root of the left side, I get d. If I take the square root of the right side, I'm going to plug that in a calculator, and I find the distance here, rounding to the nearest hundredth of a mile, is going to be approximately, I get 4.82 miles. Okay, so at this point here, Andrew is about 4.82 miles from the lodge. Okay, so we move on to the next part of the problem. The next part of the problem, we want to find the bearing to the nearest degree he should follow to return to the lodge. So if Andrew's right here, what bearing should he take to get back to the lodge? And I'm going to go ahead and erase some stuff just to kind of keep things cleaner here. These problems get a bit messy, so let's erase anything that we don't really need right here. And we'll kind of fill it in as we go. And so let's figure out what this bearing is that we're looking for, first of all. So the bearing that we're looking for is Boy, I am having a hard time. There it is. Okay. My little symbols aren't showing up very well for this PowerPoint. So if we're from where Andrew ends up here, which direction does he need to go to return to the lodge? Well, he needs to go north. If he went north, it would be going straight up this way, and then he needs to go through some angle here to return to the lodge. So his bearing is going to be north, so many degrees to the east, it looks like. So let's kind of backtrack and see what we know. Well, starting with, if I sketch a little triangle here, a right triangle, we have two different angles we're trying to find here. First of all, I want to find this little angle right here. Okay, so to find this little angle right here, I'm sketching a right triangle here. And I happen to know that this angle right here is 15 degrees from in the beginning when Andrew went south at a bearing of 15 degrees west. That gives me this little angle. And so if this angle is 15 degrees, together these two angles make 90 degrees. This angle here is going to have to be 75 degrees, which means that my angle I'm looking for here is going to be 90 degrees minus 75 degrees. This angle right here would be 15 degrees. All right. So I've got part of the angle I'm trying to find for the bearing. I have 15 degrees for this part of it. I need to find now this part right here. We're going to call this alpha. So this is the angle I'm still trying to find here, my angle alpha. Okay, so to find this angle, I'm going to have to do something I don't really like to do that much. I'm going to use the law of sines, and I'm going to use the fact that we found D was approximately equal to 4.82 miles. The reason I don't like to do that is because D is a rounded value, but I don't know of any other way to solve this problem. So we're going to need to use the law of sines, where we're going to say, well, the sine of alpha over 2 is going to be approximately equal to the sine of 120 degrees over 4.82. Okay, so if we cross multiply there, we have cross multiply and divide by 4.82. We have sine alpha is approximately equal to 2 sine of 120 degrees divided by 4.82, and then alpha itself would be approximately equal to the sine inverse of 2 sine of 120 degrees divided by 4.82. Okay, so we'll plug that in a calculator and we get alpha is approximately equal to, let's see what I got. I got 21 degrees. So hopefully if you try that, you get the same thing. So alpha is about 21 degrees here. That means we have 15 degrees and we have another 21 degrees. So our bearing is going to be, the bearing that we're looking for is north. And if we take 15 degrees plus 21 degrees, we get 36 degrees. So we're going to have north 36 degrees, and that's going to the east. So this would be our bearing. And by the way, it said to round to the nearest degree here, so that's why I didn't carry that out any further. Okay, well, go ahead and try this on your own and double check that you get the same thing. We're going to plot a polar equation next, and we're going to make a list of points that we use. Okay, so this is another thing that you should be somewhat skilled at for exams. And I'm just going to go through some points that I went ahead and chose theta values in increments of pi6. It seemed to work well for this problem, being that we're working with a cosine. So I'm going to start with, well, r is equal to 5 cosine of 3 theta. If theta is 0, 3 times 0 is 0, then the cosine of 0 is 1, and 5 times 1 is 5. Go ahead and make sure you're good on these on your own. If theta is pi over 6, if we take 3 times pi over 6, we're going to have pi over 2. So what I'm doing for pi 6 is I take 5 times the cosine of pi halves. The cosine of pi halves is 0, right? So 5 times 0 is 0. And then I move on to pi thirds. 3 times pi thirds would mean I'm taking the cosine of pi here. The cosine of pi is equal to -1, and then 5 times -1 would give us -5. If we move on to a theta value of pi halves, we're taking 5 times the cosine of 3 times pi halves. That would be 3 pi over 2. The cosine of 3 pi over 2 would be 0. So 5 times 0 is 0. For 2 pi thirds, 3 times 2 pi thirds is 2 pi. Here we're taking 5 times the cosine of 2 pi. Think of where you're at with 2 pi. You're back on the positive x-axis. So the cosine is going to be 1. 5 times 1 is 5. For 5 pi over 6, 3 times 5 pi over 6, we're going to be taking 5 times the cosine of 5 pi halves. So with 5 pi halves, we go all the way around the unit circle and then another pi half. So we're at pi halves. The cosine of pi halves is 0. 5 times 0 is 0. At pi itself, we're taking 5 times the cosine of 3 pi. So the cosine of 3 pi, where we're at, we're 1, 2, 3. We're back at pi radians. And the cosine at pi radians is going to be -1. 5 times -1 is -5. At 7 pi over 6, we're going to have 5 times the cosine of 7 pi halves. If we take 3 times 7 pi over 6, and so that takes us around the unit circle 2 times plus an additional, well, let's see, what have we got? 4 pi halves. So it takes us 4 pi halves. We'd go around once and then again 3 pi over 2. The cosine of 3 pi halves is 0. 5 times 0 is 0. And then for 4 pi thirds, 3 times 4 pi thirds would be 4 pi. So we're taking 5 times the cosine of 4 pi, which would be the same as the cosine of 2 pi, would be 1. 5 times 1 is 5. So usually I go all the way to 2 pi, but when I started graphing this, I found that it started repeating itself. So we're going to go ahead and graph here. but you'll see that after a bit, this does start repeating itself. Okay, so let me change colors. Some color that, actually green, we'll do red here. We'll do red. Okay, let's start with 0 pi. So we're at 0 radians. At 0 radians, we're going to come out from the pole a distance of 5 units. So this is the 0 radians. We come out 1, 2, 3, 4, 5. This is our first point on our graph. And then at pi 6, so here's pi over 6. And then we're going to just kind of mark this ray here. So we come out a distance of 0. So we're going to go from 0, 5. And I'm going to put arrows on this just so you can kind of see the direction we're graphing in. You wouldn't want to leave arrows on your graph, but sometimes they help with graphing. Okay, so we're at pi 6, 0. And then we go to pi thirds. So at pi thirds, this is pi thirds, but at pi thirds, we're actually going in the negative direction. So I'm going to need to come down here along the pi thirds and keep going. So at pi thirds, we're going negative 5. So we're going 1, 2, 3, 4 in the negative direction along the positive pi thirds. Positive pi thirds goes up, negative. So pi thirds goes up, so if we're going positive 5, we'd go in the positive direction. Instead, we're going in the negative direction. And so following along with our graph then, we're going to be going this way. And so maybe I'll check these off as we go. And now we're at pi halves. So pi halves, the positive direction is straight up. We come up a distance of 0. In the pi halves direction, and so we're going to go ahead and follow this through, and we're back at the pole again. Okay, and then at 2 pi thirds, the positive direction is up to the left a bit, and so along this ray, at 2 pi thirds, we're coming a distance of positive 5, which will take us to right here. Okay, so we were right back at the pole, and then we're going to go up this way, and so we've got that one taken care of. And then at 5 pi over 6, right here, positive direction up and to the left. This is a 5 pi over 6 ray. We come back to a distance of 0 from the pole. Okay, so we're coming along this way. Okay, so, and then we go to pi. So pi, positive direction is to the left. And we go a distance of negative 5 though, so we're going backwards from the pole. 1, 2, 3, 4, 5. We're back here again. So we're going to end up going back to where we started at. And now you'll see these last 2 points start repeating. So at 7 pi over 6, the positive direction is down to the left. At 7 pi over 6, we're going a distance of 0. So we'd come back actually and start repeating our graph here. And then we go to 4 pi thirds, positive direction down to the left. At 4 pi thirds, we're coming from the pole a positive distance of 5. 1, 2, 3, 4, 5. So again, we're starting to repeat our graph here. And sometimes that happens. Usually, I would say on most exam problems that I've seen for graphing polar equations, usually you do need to go all the way to 2 pi, so make sure that you keep that in mind. But for this particular problem, we didn't need to go quite that far. So, okay. So this is a rose. It's a common shape that we have. And make sure you're good with the other shapes as well. Let's go on. And here we're solving a triangle with sides of lengths 4.1, 4.8, and 6.7. And then we're going to round angle measures to the nearest hundredth of a degree. Again, I'm going to draw some triangle that doesn't have anything to do with how long my sides are. 4.1, 4.8, 6.7. To solve this triangle, we need to find the angles, right? So let's just call these alpha, beta, and gamma. We don't really have an A, B, and C here, although I guess we could figure out what those would be. So the first thing I'm going to do is if I only know the side measures and I don't know any angles, I'm going to have to, oh, excuse me. I'm going to have to use the law of cosines. I like to start with the largest angle first for the law of cosines, so let's go with beta. So we have 6.7 squared, the side opposite beta, equals the other two side lengths, the sum of the other two side lengths squared, 4.1 squared plus 4.8 squared, minus 2 times 4.1 times 4.8 cosine beta. Okay, and I think the reason I wanted to include this problem is we're solving for the angle here, and I don't know that we've done any of those yet. Well, the first thing I'm going to do then is I'm going to subtract 4.1 squared from both sides. I'm going to subtract 4.8 squared. That leaves me with negative 2 times 4.1 times 4.8 cosine beta on the right side. I'm also going to divide through by negative 2 times 4.1 times 4.8, and this would equal cosine beta. So now we're going to solve for beta by taking the cosine inverse of 6.7 squared minus 4.1 squared minus 4.8 squared all over negative 2 times 4.1 times 4.8. And we get beta is approximately equal to, and we're rounding to the nearest hundredth this time, so let's see what I got. I got beta is approximately equal to 97.36 degrees. Okay, so this is one angle. And our second angle, well, now that we found beta, we could use the law of cosines again, and actually it would probably be more accurate to do so, but I'm going to go ahead and jump to using the law of sines. So for our second angle here, we'd use the law of sines, and let's see if we can find alpha next. So let's look at the sine alpha. Alpha is opposite 4.8, and we're doing approximate values now, right? Because we're going to use this rounded value for beta. And so sine alpha over 4.8 is approximately equal to sine of 97.36 degrees over 6.7. And so we'll cross multiply, and we're going to end up with sine alpha equals, if we cross multiply, we have, I should put approximately equal to, sine of alpha is approximately equal to there we go. It would be 4.8 times the sine of 97.36 degrees divided by 6.7. From that, I'm going to find alpha by taking the sine inverse of 4.8 sine of 97.36 degrees divided by 6.7. And so I get alpha is approximately equal to, I hope I'm doing the right one here, 45.28 degrees. Okay, And then we have one more to go. I'm just going to find our last angle here, gamma, by taking 180 degrees minus beta minus alpha. And so from that, I get that gamma is approximately equal to, I should have said approximately here as well. Gamma is approximately equal to 37.36 degrees. Okay, and I actually solved earlier for gamma using the law of sines, and I got a different value. I actually got 37.37 degrees. So I'm going to tell you guys, when you do take an exam, let me know if you have an issue like that where you round and you use legitimate rules here. It's a rounding error, and really, we probably shouldn't be rounding. We shouldn't use the rounded value here to find other values with the same accuracy of decimal places. We should be carrying beta out a little further if we're going to use beta for finding other values. So anyway, okay, well, let me know if you have any questions on this. We're finding nth roots yet, so we have one more complex number thing. I guess I kind of just scrambled questions here, which is how you would probably see them on a regular exam. But what we're doing here is we're finding nth roots. We're given that z equals r cis theta, and we're finding the nth roots of z. And the formula for that is each root is w sub k equals the nth root of r cis theta over n plus 2 pi k over n for k equals 0, 1, 2, and all the way up to n minus 1, whatever that happens to be. A couple things to note are here is the modulus of z. Okay, and what else was I going to say? So n is the number of roots that you have. We'll do an example of this in just a sec. So your roots are going to be, the first root would be w sub 0, then w sub 1, then w sub 2. Say you have 3 roots. Those are the roots you'd have. W sub 0, w sub 1, w sub 2. But anyway, we'll go ahead and work through a problem with this. We're going to find the fourth roots of negative 16, and we want here to leave our answers in polar form. So to find the fourth roots of negative 16, well, the first thing I'm going to do is I'm going to write my formula. W sub k equals, to see what we need to find, equals the nth root of r cis theta over n plus 2 pi k over n. Okay, so once we get this formula, we can go to town, but we need to get this first. Well, for our particular, for the number we're working with here, we have z equals negative 16. Okay, this is in rectangular form. You can think of that as negative 16 plus 0i if you wanted to. And so the modulus of z here would be the square root of 16 squared plus 0 of negative 16 squared plus 0 squared. And we're going to end up with the modulus being equal to 16. Okay, so we have the modulus of z. And I did that kind of sloppy there. Let me fix that. So we have the square root of 16, negative 16 squared plus 0 squared. And you would get 16 there for the modulus. And then we need to also find the angle. We need to put z into polar form. It's in rectangular form right now, so to put it in polar form, we also need the angle of z. Well, let's see where this angle ends up at. So negative 16, we have a real axis and we have an imaginary axis. Negative 16 is on that negative real axis, right? So I can just look at that without messing with the tangent. I can see that my angle theta here is going to be pi. Okay, so z, written in polar form, is going to be 16 cis pi. Okay, now if I'm trying to find w sub k, I need to find n. Well, we're finding the fourth root, so we have n equals 4. R is equal to, R is the modulus of z, so R is equal to 16. What else do we need for our formula? We need theta. We have theta equals pi. I think that's about it, right? So let's see if we can figure this out. So to find my formula that I'm going to use to get the roots, I have w sub k equals n was equal to 4. So we have the fourth roots of r, where r was equal to 16. Then we have cis. And we have theta. Theta is pi over n. N was 4. Plus we have 2 pi k over n, and n was 4. So we can simplify this formula a bit. W sub k is going to equal, the fourth root of 16 is 2. So we have 2 cis pi fourths plus pi k over 2. And I think this will be fairly simple. Our first root, we start with 0. So our first root, we're letting k equal 0. We're going to have 2 cis. And then you're going to have pi fourths plus pi times 0 over 2. This is just going to be pi fourths plus 0. So our first root is pi over 4. Our second root, we're letting k be equal to 1. We have 2 cis. And we'd have pi over 4 plus pi times 1 over 2. So we'd have pi fourths plus pi halves. That would give us 3 pi over 4. The third root, w sub 2, equals 2 cis. And this time we're going to have pi over 4 plus pi times 2 over 2. And so we just add pi fourths plus pi. That would give us 5 pi over 4. Our last root is w sub 3. We have 2 cis. And then we'd have pi over 4 plus pi times 3 over 2. So that would be 3 pi over 2, which is 6 pi over 4, plus 1 pi over 4, 7 pi over 4. And these are our 4 roots of negative 16. All right, so let's go on. We should be getting near the end here. We have just a couple more problems to do. In this next problem, I want to plot the points whose polar coordinates are given and then label the points on the graph. I want to find an additional pair of polar coordinates that identifies each point. So let's start with point A, which is the point 3, 5 pi over 4. I'm going to start by finding 5 pi over 4 right here. And we're going to come out along this ray, 5 pi over 4, a distance of 3. So here we go, 1, 2, 3. And we found our first point. I'm just going to write A for our first point here. The other thing we want to do here is we need to identify this point with another pair of polar coordinates. Well, that's easy enough. We can just let r be equal to negative 3. And if r equals negative 3, that means that if I went along the same ray, or the same line, I guess, I'd be going, instead of going positive 3, I'd be going negative 3. Well, this angle that we have here is pi fourths. So let's try it. We have negative 3 pi fourths. Think about it. If I started out coming over to the pi fourths ray, instead of going in the positive direction, if I go 3 units in the negative direction, I would arrive at my point A. So that works. So another way to identify that point is as negative 3 pi fourths. Let's look at our next point, which is 4 negative pi thirds. I'll change colors here. So this time I'm going to figure out where is negative pi thirds. So if we start at 0 and we go negative pi thirds, we'd be going in the clockwise direction. We'd end up at 5 pi over 3 here. And I'm just going to put a little dash along this ray here that takes me to 5 pi thirds. And so we come out how far? So at negative pi thirds, we're going a positive distance of 4. So the positive direction is down and to the right a little bit. And so from the pole, we're going down 1, 2, 3, 4 units. And this right here would give us our point B. We need another name for that point B. Well, let's just say instead of 4, let's say we have negative 4. And then what ray would I be going along? Which direction would I be going to so that negative 4 would take me to this point B? Well, easy enough. Let's just come up and extend our little dashed line in the opposite direction from the pole. So that, what angle are we at there? 2 pi thirds. Let's try it and see if it works. Okay, so if we start out at 2 pi thirds as being positive direction up and to the left, and instead of going positive 4 from the pole, we're going negative 4 from the pole, we would end up at that point B, so this works. Okay, we've got one more to go, and this time we have the point negative 5, negative pi halves. So this time, if I start at negative pi halves, well, negative pi halves takes us down here to 3 pi halves, same place. So we're going negative 5 though. So the positive direction along this negative pi halves ray would be down. And then we want to go negative 5. So we're going the opposite direction, which brings us up to this pi halves ray. And we're going 1, 2, 3, 4, 5. So if the positive direction is down, the negative direction is going to be up here. And so this is our point C. Another way we could write that, well, let's start by just changing negative 5 to 5. And so if I want to get to this point C, and I want to go in the positive direction from the pole, well, I'm going to be coming up along this pi halves radian. So my angle here would be positive pi halves. Seeing if it works, if we go pi halves, and then we go positive 5 from the pole, we do end up at that point C. Okay, so let's move on. And what I want to do next is convert an equation from polar to rectangular coordinates. There are some magic formulas you can keep in mind that help with this. And there's 4 of these. If you know these 4 formulas, they'll really help you anytime you need to convert between rectangular and polar. Starting with, we have r equals 2 sine theta. And there's some things I can do. One I think that might help here is if I see sine theta, that's really close to r sine theta, right? So, and on the left side I have r. I'm just going to multiply both sides by r here. And rewrite that as r squared equals 2r sine theta. And I'm trying to turn this into rectangular coordinates. So I can write r squared as x squared plus y squared. And I can write r sine theta as y. Okay, well, we actually have a formula here, but let's make that formula look a bit nicer. I'm going to pull the 2y to the left side. So I have x squared plus y squared minus 2y. I can see where I'm headed, so I'm going to put a 0 on the right side, but leave a little bit of space, because what we want to do here, I think, is complete the square on y squared minus 2y. I can do that by throwing some parentheses around here and adding the number I need to complete the square. If I take negative 2 divided by 2, I get negative 1, and then squaring that, I get plus 1. I'll add 1 to the right side as well. And we can now write this equation as x squared plus y minus 1 squared equals 1. This is a circle. If you think about it, that circle has center of 0, 1, and it has a radius r squared is equal to 1. That means our radius is also 1. Square root of 1 is 1. All right, so we have a circle here. Let's do one more problem, and I think you'll be good. This last problem, we're going to convert the equation from polar to rectangular coordinates. And here we're going to use these same formulas again, see what works. All we have here is a theta. Well, there's 3 different formulas with theta in it. And only one I think that's going to work really well here. And that would be if we had tangent of theta, we could turn this into y over x. Well, what I can do here is rather than multiplying both sides by a number, I can actually take the tangent of both sides. And so I have the tangent of theta is equal to the tangent of negative pi fourths. If you think of negative pi fourths, we're in the 4th quadrant. The tangent in the 4th quadrant is negative. And the reference angle being pi fourths, the tangent of negative pi fourths would be negative 1. Now I'm going to go back to my formula here, and I'm going to write tangent of theta as y over x. I have y over x equals negative 1. That gives me y equals negative x. This is an equation you should be familiar with. In fact, if you think of theta being equal to negative pi fourths, that would give me right here all the r values along that line from which we get from angle negative pi fourths. This is also the line y equals negative x. So hopefully that makes sense, how these 2 equations give us the same line. And I believe that's all we have for this review. Please let me know if you have any questions. While you're reviewing, work through your worksheets. Also work through the problems from old final exams that you'll find there's a list of those in your course under the exam review. And let me know if you have any questions. I'll get back to you as quick as I can and hope you do well.